What was the world's top-selling drug in 2023? Maybe the magic weight-losing drug semaglutide, or better known as Ozempic? Or the COVID vaccine, perchance? Nope. 2023's top-selling drug was an antibody, Keytruda, with about $25 billion in sales, $27 billion projected for 2024. In fact, 5 of the top 10 best-selling drugs in 2023 were antibodies. Antibody therapies revolutionized medicine. We've long known that they can. The problem has always been how to make them the right way and at industrial scale. Today, it is done with the help of a hamster, or rather, its cells. In this video, the incredible story of the hamster that revolutionized medicine. This is one of my favorite videos of the year. Antibodies. What are they? I shall cite the canonical source of all foundational scientific knowledge for people my age, the American TV show Magic School Bus. In a classic episode, the Magic School Bus enters student Ralphie's body as he fights a cold. Inside, they find these Y-shaped sticks. The sticks attach to foreign bodies like bacteria and Magic School Buses, signaling white blood cells to come destroy them. That pretty much sums it up. Those are antibodies, or sometimes also called immunoglobulins. Humans and other vertebrates produce them in response to molecules called an antibody generator, or antigens. In humans, antibodies are made by a line of B lymphocytes, or B cells. These B cells descend from stem cells in the bone marrow. They then travel to the spleen where they are activated and start making antibodies. A strange name was given by the Nobel Prize-winning German physician Paul Ehrlich, who in 1897 proposed the idea of these quote-unquote side chains that can bind to toxins. He called these chains an anticorpor, or antibody, during a lecture, presumably as a placeholder. But the name, like the thing itself, stuck to the antigen of popular sentiment and hasn't let go since. We've long known that the antibody plays an important role in the human immune system and can be used for medicines. The problem is that we cannot cultivate human B cells in a culture for very long. So we need another way to produce enough antibodies for treatments. One early method we tried was using donors. This is how it worked. We slowly inoculate an animal, like a horse, with a disease. The horse naturally builds up antibodies to the disease microbe as an immune response. After some time, we harvest the serum from the horse, purify it, and use that for treatment. The German physiologist Emil von Behring won the 1901 Nobel in Medicine, the first ever awarded, for discovering an antitoxin to lower the mortality of the disease diphtheria, which once regularly killed 50,000 children a year. Antibodies and such antitoxins can neutralize toxins or kill bacteria directly. The issue with this serum therapy, as it was so called, was that different donor B cells react differently to inoculations based on their own special history. All that diversity does not give you reliable antitoxin activity. Moreover, impurities like horse proteins in the donors can cause a condition called serum sickness, or worse, even death, as it famously did in 1901 when a donor horse caught tetanus and passed it to children, of which a dozen died. There were other issues with manufacturability. The use of an animal donor, like a horse, chosen for their high blood content, was a bit of a hassle. With the subsequent discovery of antibiotics, the use of serum therapy faded, but people still occasionally searched for a way to artificially produce pure doses of antibodies at industrial scale. The two-time Nobel Prize winner Linus Pauling made headlines in the early 1940s when he announced a method for producing artificial antibodies and tried to patent it. However, other researchers could not replicate his experimental results, and the idea fell away. Monoclonal antibody is a fancy term that simply refers to exact copies of a single antibody, single clones. This medical breakthrough begins in the 1960s with work done on tumors called myelomas, which are cancers of the plasma cells. Being a cancer, these myelomas infinitely reproduce from a single progenitor. Myeloma cancer cells produce a faulty type of antibody called myeloma protein. You can technically call them monoclonal antibodies, but Since they are the demented cries of a broken cell, myeloma proteins are not useful for medicine. But what if we change that? Two scientists, Cesar Milstein and George Kohler, knew about this special virus called a Sendai virus. The virus has a funny ability. It can fuse two cells together, thing style, by merging their membranes. That is actually quite horrifying, but it got Kohler thinking about whether they can fuse mouse myelomas with mouse B cells to create hybrids. Milstein, to his credit, didn't think this was crazy, so they inoculated a mouse with an antigen, the red blood cells of a sheep, which then caused it to make antibodies against those sheep cells. They then fused that inoculated mouse's spleen cells with mouse myeloma cells using the Sendai virus. The experiment worked on the first try, creating a bunch of Cronenbergs called hybridomas, with both the longevity/hardiness of cancer cells and the antibody-making capacity of B cells. Remarkably, Milstein never attempted to patent the hybridoma method, either because of a miscommunication with the organization making the application or because he never considered its full commercial potential. But it all worked out in the end. A mere 10 years after the publication of their paper, Kohler and Milstein won 2/3 of the 1984 Nobel Prize in Medicine. Monoclonal antibodies triggered massive excitement. As early as 1980, people were talking about using MABs, as they were called, in immunology treatments, with the press calling them quote-unquote magic bullets. Probably not the best way to set expectations. The first treatment was approved in 1986, Murimonab CD3 or orthoclone OKT3, an antibody treatment that helps prevent the human body from rejecting a kidney transplant by binding to the CD3 complex on the surface of T cells. This was indeed groundbreaking and expected to save thousands of kidneys that would otherwise be lost. But the hype soon hit reality. Using mouse hybridomas to produce the antibodies caused about 5 to 10% of the patients to suffer complications, some of which can be quite serious, like an allergic shock. There were other issues. The hybridomas were genetically unstable. The mouse-made antibodies did not last long inside the human body, necessitating large, frequent doses, and the human immune system did not recognize the antibodies, causing ineffective performance. Throughout London in the 1980s, millions of dollars were invested in startups developing monoclonal antibody therapies. Many of them turned out to be duds. The 15 years after the 1975 Nobel-winning discovery yielded just one US-approved treatment, orthoclone. One former biotech exec in the space murmured, "Monoclonal antibodies were described as magic bullets. There was just one problem with the story. It wouldn't work. It was molecular snake oil." If monoclonal antibodies were to ever fulfill their potential, then we must produce the right ones better. And here is where we must change the subject and introduce the Chinese hamster. The Chinese hamster is a little rodent from northern China or Mongolia. It looks like a regular hamster, albeit maybe a little skinnier and a slightly longer tail. It is grayish-brown in nature, and the male has a fairly large scrotum for its size. All of this will be on the exam. The Chinese hamster first entered the laboratory in 1919 thanks to the work of Dr. E.T. Xie of Peking Union Medical College. He infected them with pneumococci, a major cause of pneumonia, for an experiment. These hamsters have long been regarded by Chinese farmers as a pest in the fields. They have these big cheek pouches for carrying off tons of grain each year. But as it turns out, Chinese hamsters were quite vulnerable to various human diseases, making them good for study. So researchers infected them with tuberculosis, influenza, rabies, diphtheria, and black fever, which makes me kind of feel for these little guys. The issue, however, was that each Chinese hamster had to be caught in the wild. They did not breed in captivity, being a rather solitary and bellicose animal. Female and male hamsters often fight, the females especially more so. In the late 1920s, Harvard Medical School tried to grow a colony of 150 hamsters. Researchers built burrows in the basement and everything, but the hamsters failed to reproduce despite surviving the brutal Boston winter. Take that, Harvard. This became a problem in the waning days of the Chinese Civil War, which would shut off the world's only supply of Chinese hamsters. In 1948, as Mao Zedong's communist forces sweep across China, Dr. H.C. Hu of Peking Medical Union College in Beijing sends a crate of 20 hamsters, 10 male and 10 female, to Dr. Robert Briggs Watson, an American scientist studying malaria in Nanjing. On December 6, 1948, Dr. Watson is hand-delivered the hamsters as he and his staff are packing up their lab for shipment to Taiwan. With the communists approaching the city from just across the Yangtze River, Watson decides to leave. He packs his precious box of loud, chittering hamsters into an overstuffed station wagon and sets out at 5:45 a.m. in the ice-cold rain with a bottle of brandy, a book of prayers, and an old Colt 45. After a harrowing 11-hour drive to Shanghai via a roundabout way through Suzhou and Hangzhou, avoiding mudslides and roving bands of communist troops, Dr. Watson and his 20 hamsters take literally the last Pan Am flight out of Shanghai to the United States. In April 1949, after peace talks fail, the People's Liberation Army crosses the Yangtze River to conquer Nanjing and the rest of the mainland. The People's Republic of China is declared soon after. Watson brought the happy hamsters to the renowned rodent breeder and supplier Victor Schwenker in New York and promptly forgot about them. Years later, the Communist Party tried Dr. Watson in absentia and condemned him to death for allegedly conducting germ warfare against the Chinese during the Korean War via hamsters. A ridiculous claim. But Dr. Hu was also convicted of helping the Americans and was sent to a re-education camp. These accusations resurfaced during the Cultural Revolution a decade later. After one vicious beating by the Red Guards, Dr. Hu and his wife committed suicide in 1966. With great effort, Schwenker tames the hamsters and breeds a healthy colony. A second supplier emerges by 1954. George Yergenian, a former Harvard student, discovers that the hamster's low chromosome count made it ideal for genetic research. He discovers his own secrets to breeding the Chinese hamster, which apparently involve a reverse illumination scheme, and establishes his own colony descended from Schwenker's. Moreover, a random genetic quirk from generations of inbreeding created a new lineage of diabetic hamsters suffering the same type diabetes seen in humans. This made them useful for diabetes research and maintained their lineage in universities and labs. In 1957, Theodore Puck, a researcher at the University of Colorado, is developing techniques for immortal cell lines, kind of like the now famous Henrietta Lacks HeLa cell line. Interested in the Chinese hamster's rather small chromosome set, he got a single female hamster from Yergenian, a descendant of Dr. Watson's original 20. Carefully, he extracted some cells from its ovary and cultivated them in a medium for 10 plus months. They grew over the generations without much observable differences. In other words, they had spontaneously gone immortal. Based on this work, Puck created the famous Chinese hamster ovary, or CHO, K1 line. Other lines were soon developed, and throughout the 1960s and 1970s, CHO cells were well known in the genetics community in those days for their big chromosomes, hardy cell cultures, and easily identifiable mutations. In 1976, a VC named Robert Swanson and a biochemist from UC San Francisco named Herbert Boyer founded a company called Genentech. Boyer was a pioneer in recombinant DNA techniques, a newly discovered form of genetic engineering. Genentech soon made headlines for using recombinant DNA techniques to force E. coli bacteria into producing human insulin and growth hormone. But when Genentech then tackled TPA, an enzyme used within the body to dissolve blood clots, the E. coli failed to produce. The same happened with other proteins too, like a new hepatitis B vaccine. Genentech determined that E. coli, a mere simple bacteria, could not handle these complicated proteins. One key missing thing being the ability to perform an enzymatic process called glycosylation, where sugars are attached to new proteins to make them fold properly for better stability. Looking for a more effective biofactory to produce these more complicated proteins, the Genentech guys hear about a new line of CHO cells with a nifty trick. In 1976, a Stanford graduate student named Fred Alt discovered a quirk. There's this cancer drug called methotrexate. It kills cancer cells by cutting them off from an enzyme called DHFR. The cancer cells can quickly grow resistant to the drug by rapidly amplifying a gene to produce DHFR. It is then thought to use this natural behavior to amplify genes throughout some mammalian cells. If you took a line of CHO K1 cells and delete their DHFR genes, the cells cannot survive when hit with the methotrexate. But if you introduce a gene that codes for DHFR, the cells will rapidly take up that gene and add it to their genome. So in that case, let us attach a free rider gene producing a desired protein to the DHFR gene. The CHO cells will snatch up both genes like their lives depend on it and amplify them. A few rounds of methotrexate later, and you have a cluster of CHO cells producing a protein of your desire. Genentech learned about these techniques and set up big 10,000-liter vats of CHO cells producing TPA enzyme at scale. In 1987, Genentech TPA was approved and other bioengineering companies followed on, rapidly adopting the CHO cell platform for making all types of complex proteins, like antibodies. The final step in completing the circuit was to make the rat and other rodent antibodies more human-like. By reducing the number of non-human sequences, there's now even an H-score used for judging a sequence's humanness, we can produce humanized antibodies that the human immune system can actually accept. In 1997, Genentech and IDEC Pharmaceutical launched Revolutionized, a monoclonal antibody used for treating autoimmune disease and some types of cancer. And then the year after, 1998, the FDA approved Genentech's blockbuster antibody trazimab, better known as Herceptin. Targeted at certain aggressive breast cancers, the drug revolutionized treatment of what had once been a certain death sentence. Early trials with Herceptin were so successful that advocates bullied the FDA into fast-tracking its approval. It remains the gold standard in HER2 breast cancer treatment. Production of both antibodies ramped up in Genentech's facility in South San Francisco, made with CHO cells, of course. I recently heard that they closed this legacy production center in 2023, laying off 265 people. Sad. Today, the CHO cell platform dominates the mass production of antibodies and other recombinant proteins. 71 new pharmaceuticals were introduced between 2014 and 2018. Over 80% were manufactured by CHO cells, with E. coli a distant second. The ecosystem is undeniable. The FDA is familiar with CHO, which reduces regulatory uncertainty, and thanks to 30 years of fine-tuning, CHO cells have high yields and growth rates, contributing to production costs falling from $10,000 per gram to just about $100. Try asking a bio-VC to back a mAb therapy made outside of the CHO platform. You will get a very hard no. I want to thank Dr. Darren Nesbitt of the University College London for suggesting this brilliant topic and for graciously taking the time to walk me through it. If you're interested in this kind of stuff, check out his 1-year synthetic biology postgrad program, link in the description. We often skip over the manufacturing of medicines, but we shouldn't. One reason why revolutionary gene therapies like Lenmeldy are so expensive, $4.5 million for a single dose, is because we lack a CHO-like scalable method for manufacturing them. Each gene therapy is basically a custom-made Lamborghini. And a final point on antibodies, even now, as they dominate the top 10 board, I don't think they have even begun to peak. Something that I am very excited about is the forthcoming merger of antibodies and cell-killing drugs, antibody-drug conjugates. It is basically laser-guided chemotherapy using specific antibodies to put warheads on cancer cell foreheads. The future of medical treatments has never been so bright, in part thanks to monoclonal antibodies in the hamster cells that make them. Alright everyone, that's it for tonight. Thanks for watching. Subscribe to the channel, sign up for the Patreon, and I'll see you guys next time.